everyone. Today, let's talk about session 4.1, LU factorization. So LU factorization finds a lower triangular matrix L and an upper triangular matrix U so that our original matrix A equals L times U. Okay, so what is lower triangular matrix? Well, lower triangular matrix is a square matrix. So this is the diagonal. Okay, so the upper triangular entries, they are just zeros. Okay, the only non-zero entries are the lower triangulars and the diagonals. And the upper triangular matrix is the non-zero entries are on the upper triangulars, and the lower triangulars is gonna be 0. So far, so good. So L is like lower L, right? And U is like upper triangular upper U, okay? So A equals LU. The LU factorization is not unique. The 3 most common forms corresponds to 3 different assumptions about the diagonal elements of L and U. We're going to talk about all 3 of them, okay? So the LU factorization has 2 main use. First, it can help us to solve a linear system of equations, especially when the system AX equals to B must be solved repeatedly using different values of B. So do you remember, given a linear system, what do? We use the Gaussian elimination. We perform a sequence of elementary row operations until we get to the echelon form, right? But if we have the LU factorization, we can simply just do back substitution. Okay, and the second main use for the LU factorization is very convenient to find the determinants of it. Okay, so do you still remember the determinants of a product equals the product of the determinants? And the product of a triangular matrix is just the product of its diagonal elements. So it makes it so convenient to calculate the determinants. We just look at the diagonal elements of L and the diagonal elements of U, and then we just multiply them together. Then we get the determinants of A. Alright, so now let's talk about the 3 most common forms of the LU factorization. First one, we have the Doolittle's method, where we assume the diagonal elements of L are 1. And the second one is the Crowd's method. We assume the diagonal elements of U are 1. And the Kolsky method, we assume the diagonal elements of L and U are equal. Well, in this case, we require the matrix A must be symmetric in order to have a Kolsky method. Okay, so let's look at the following methods. First one, Doolittle's method. Okay. So Doolittle's method, we assume that the diagonal elements of L is 1. Okay, so A equals L times U. So let's look at this example 1. We find the LU factorization of the following matrix using the Doolittle's method. Okay, so let's set it up. We have set up the L, the diagonal is 1, okay? And then the upper triangles are 0. And the lower triangles, this guy is in the second row, the first column, so we call L21. This is L31. This is L32. Okay? And then U is the upper triangular, so this is U11, U12, U13, because it's in the first row, right? This is U22, this is U23, this is U33. And that equals our matrix A. So 1, 2, minus 1, 2, 3, 0, minus 3, 1, and 4. So far, so good, everybody? Okay, And then to calculate, so here, how many unknown do we have? We have 3 times 3, 3. We have 9 unknowns here. So we should get 9 equations to solve 9 unknown. Okay? So how do we get those equations? Well, let's look at each entry. First row times first column give us 1, okay? And actually, when you write down those equations, I hope you can write them down in this order, like the matrix. Okay, imagine this is like a big matrix. Then you put the like this entry is correspond to this guy. So you put the equation in the corresponding spots. Okay, and it's easier for us to organize and find the entries. So far so good, everybody? Okay, the first one, we have 1 times u11 equals 1. Is that okay? 1 times u11 plus 0 times 0 plus 0 times 0, we get that is 1. So that is the same as u11 equals 1. Okay? Second one, first row times the second column. So 1 times u12 plus 0 times u22 plus 0 times 0, that equals 2. So we get u12 is 2. Okay, let's continue. First row times third column. 1 times u13 equals minus 1. So u13 equals minus 1. So each equation, we should be able to solve one unknown. Okay? And then this spot, we use the second row times the first column. Okay, so we get L21 times U11 plus 1 times 0 plus 0 times 0, that equals 2. But because we already know U11 is 1, right? So we can plug in here, then we get L21 equals 2. Okay? And then this spot, we use second row times second column. So L21 times U12 plus 1 times u22 plus 0 times 0 equals 3. Well, L21 is 2, u12 is 2, u22 right here is our unknown. Oh, 2 times 2 is 4. So u22 is like 3 minus 4, which is negative 1. So far, so good, everybody? Okay. And here we use the second row times the last column. L21 times U13 plus 1 times U23 plus 0 times U33 equals 0. L21 is 2, U13 is minus 1 plus U23 equals 0. So U23 is, well, that is negative 2, move to the other side, is just 2. So far, so good, everybody? Okay. Next, we use the third row times the first column. So we get L31 times U11 equals negative 3. U11 is 1, so L31 equals negative 3. So far, so good, everybody? Okay, next. Next we have the third row times the second column. So L31 times U12 plus L32 times U22 equals 1. Okay, L31 negative 3, U12 is 2. L32 is our unknown. U22 is minus 1. So we get L32 times minus 1 is 1 plus 6. Right? 1 plus 6 is 7. So L32 is minus 7. Okay. Last one, we have last row times the last column. L31 times U13 plus L32 times U23 plus 1 times U33 equals 4. L31 minus 3, U13 minus 1, L32 minus 7, U23 is 2, and U33 is our unknown. So we get 3 minus 14 plus U33 is 4. U33, well, 3 minus 14 is negative 11. Move to the other side, become 4 plus 11, which is 15. So far, so good, everybody? Okay, now what is our L? Well, so remember, look at this spot. The funny thing is, this is the L, right? And this guy, we're gonna put it here. This guy is actually here. This guy, L32, is minus 7. So the position match with the position in the matrix. Okay, that's why I suggest you to organize this way. So when you put down the number, the position of the equation, the numbers is exactly the positions of the entries in the matrix. Sorry, the diagonal entries are ones. Okay, this is L. And then how about U? U is, oh, you look at this, right? This is our U, right? U11 is 1, U12 is 2, and then minus 1, and then these guys zeros. This is minus 1, this is 2, this is 15. See, it's very easy to find the numbers. So far, so good, everybody. Let me use a different color to emphasize. Then you can see it more clear. So let me use blue. So this is separate them. Okay, and that will give us the U values. All right. Okay, so now we have found an LU factorization for A. Okay, and this is our L, this is our U. Let me ask you a quick question. What is the determinant of A? Well, it's just determinant of L times determinant of U. Determinant of L, because the diagonal elements are just ones, so just multiply all the one together. And the diagonal element of U is 1 minus 1 and 15. Now you can see easily what's the determinant. Minus 15. See, A is a 3 by 3 matrix, but now when we compute the determinants, super easy. Just look at the diagonal elements and multiply them together. So far, so good, everybody? Okay, that is Doolittle's method. Let's continue. So Doolittle's method, we assume the diagonal elements of L are 1. And the Crowd's method is like the opposite. We assume the diagonal elements of the U are 1. Okay? Alright, let's see what happened. And the methods are very similar. So we first set it up like L11, 0, 0, L21, L22, 0, L31, L32, L33. Okay? And then U, diagonal elements are 1, and the lower triangular is just zeros. And then we have U12, U13, U23. That equals our matrix A. A is 1, 2, minus 1. 2, 3, 0, minus 3, 1, and 4. So far, so good, everybody? Okay, now let's see. So we also separate 4 region, like a big matrix, right? Each region we're gonna deal with 1 equations. So here we also have 9 equations and 9 unknown, right? Okay, first one, we use the first row times the first column. So L11 times 1, that equals 1. Oh, L11 equals 1. So far, so good, everybody. And then we have first row times the second column. L11 times U12 plus 0 times 1. Ooh, okay, so that equals 2, right? And L11 is 1, so we get U12 is 2. Next, we have the first row times the third column. So we have L11 times U13 equals minus 1. But L11 is 1, so U13 equals minus 1. Let's continue. Use the second row times the first column. So we have L21 times 1, okay, equals 2. So L21 equals 2. Next, we use the second row times the second column. L21 times U12 plus L22 times 1 equals 3. L21 is 2, U12 is 2, plus L22 equals 3. Well, L22 is like 3 minus 4, so that is negative 1. Okay, and then here we use the second row times the third column. L21 times U13 plus L22 times U23 plus 0 times 1, that equals 0. L21 is 2, U13 minus 1, L22 is minus 1, U23 is our unknown. Oh, we can both sides divided by minus 1, and then so U23, we move the 2 to the other side, become minus 2. So far, so good, everybody. Okay, let's continue. Use the third column multiplied by the first row. Oh, sorry. I mean the third row multiplied by the first column. L31 times 1 equals minus 3. So L31 equals minus 3. And then multiply by the second column. L31 times U12 and plus L32 times 1 equals 1. L31 negative 3, U12 is 2. And then L32 is 1. So L32 is, well, that is negative 6. Move to the right, becomes 6. 1 plus 6 is 7. Finally, last row times last column. L31 times U13 plus L32 times U23 plus L33 times 1 equals 4. L31 is negative 3, U13 is minus 1, L32 is 7, U23 is negative 2, L33 equals 4. 3 minus 14 plus L33 equals 4. Well, that's negative. That's negative, negative 11, right? Move to the right becomes 15, right? So, ooh, we're done. And let's put down our L and our U. So what is L? Well, what is the line separate them? Okay, L is, see, this is the spots separate them. Okay, what is L? Well, this is 1, and then zeros, 2, minus 1, 0, minus 3, 7, and 15. So far, so good, everybody. U is 0, 2, minus 1, 0, 0, minus 2, 0, 0, 0. So far, so good, everybody? Okay, so keep those in mind. Do you realize this L and U and the LU from our previous examples, they are different? Okay, so there are different LU factorization of the same matrix. See, so we can see the LU factorization is not unique for a given matrix. If we use different methods, then we just gonna get different LU factorization. Okay, so I make the same error again. The diagonal elements must be 1s. Okay, sorry. Yes. So this is a mistake that we might make easily. So always keep in mind. Don't forget to put the 1 on the diagonal elements in the U for the Krauss method. Okay, so we have a part B of this problem. Use the factorization to solve AX equals to 1 minus 1, 0. Okay, so how do we solve it? So remember, if we can solve it using the Gaussian elimination, but we need to do a lot of elementary row operations. But here, with the help of the LU factorization, so we want to solve AX equals to B, right? And what is our B? Let's copy it down here. B is 1 minus 1, 0. Okay, so this guy, A is LU. So you can think of this guy is Y. So the first step, we want to solve Ly equals the B. Okay, second step, after we solve the Y, we can solve UX equals Y. Okay, so let's look at the first one. Ly equals 1 minus 1, 0. Let's see here. So what's L? 1, 0, 0, 2, minus 1, 0, minus 3, 7, 15. Y is like Y1, Y2, Y3 equals 1 minus 1, 0. Okay, so let's do substitution. So the first row, we have 1 times Y1 is, so the first row, 1 times Y1 is just 1. So Y1 is just 1. Second row, we do 2Y1 minus Y2 equals minus 1. So what's Y2? Y2, move Y2 on the right and move 1 to the left. It becomes 2Y1 plus 1. But Y1 is 1. So 2 plus 1 equals 3. The third row, we get minus 3Y1 plus 7Y2 plus 15Y3 equals 0. Okay, now let's plug in. Y1 is 1, so minus 3. Y2 is 3. 7 times 3 is 21 plus 15Y3. Okay, 15Y3. This is like 18. When we move 18 to the other side, become minus 18. So Y3 is minus 18 over 15. The common factor is 3, so 6 over 5. So now we can see Y equals, Y1 is 1, Y2 is 3, Y3 is minus 6 over 5. Okay, so now here U is 1, 2, minus 1, 0, 1, minus 2, 0, 0, 1. Now we have x1, x2, x3 equals my y, 1, 3, minus 6 over 5. Okay, so the LU factorization helps us to save the steps of the Gaussian elimination. So we just can directly plug in and we can solve. But it's like 2 steps of the substitution, right? Here we have like the forward substitution, and here we have the back substitution, right? The back substitution, we look at the last row first. Is x3 equals minus 6 over 5, right? So that's back substitution, and then we look at the second row. Second row is x2 minus 2x3 equals 3. So x2 equals 2x3 plus 3. Well, 2x3 is minus 12 over 5 plus 3. 3 is like 15 over 5. Well, 15 minus 12 is 3 over 5. And then we look at the last row, first row. First row, we have x1 plus 2x2 minus x3 equals 1. Right? And let's see. So x1 equals 1 minus 2x2 plus x3. 2x2, so 6 over 5, x3, so minus 6 over 5. 1 is like 5 over 5, right? 5 over 5 minus 12 is negative 7 over 5. So far, so good, everybody. So finally, oops, I ran out of space here. Let me see. I can. So x finally, x1 is minus 7 over 5. X2 is 3 over 5. X3 is minus 6 over 5. So far, so good. So it's like we omit we save the steps of the Gaussian elimination, but here we have the 2 steps of the substitution. One is like forward substitution, the other one is back substitution. Okay, so forward means you look at the first row, second row, third row. Okay, and then the back substitution is last row, second row, first row. All right. So now we have talked about the 2 methods, the Little's method and the Krauss method. And we also talk about the 2 main use of the LU factorization. One is computing the determinant. The other one is use it to solve the system of equations. Okay, so let's continue to talk about the Kolsky's method. Okay, so Kolsky's method. Before we talk about the Kolsky method, let's talk about some definition. A matrix A is symmetric if A equals transpose of A. Well, let me give you an example. Let's look at 1, 2, 3, 4, 5, 6, and 7, 8, 9. This is not symmetric. Symmetric means, well, let's say you have this on your diagonal elements. If this is 2, 3, 6, this guy is like a mirror, right? Then this guy should be 2, and then this guy should be 3, and this guy should be 6. So this guy is like, the diagonal is like a mirror. Is like a mirror. So far, so good, everybody. So this guy is symmetric. The transpose equals itself. Next, a matrix is positive definite if for any non-zero vector x, x transpose times A times x is greater than 0. Okay, that's positive definite. If A is real and symmetric, then the following are equivalent. Okay, so if A is a real, so all the entries are real numbers, and if A is symmetric, then the following are equivalents. A is positive definite, or all of the upper left submatrix of A have positive determinants, or all of the pivots of A without row interchange are positive, or all of the eigenvalues of A are positive. Okay, so we know all 4 of them are equivalent. But which one shall we check? Well, we check this. This is the easiest to check, okay? Because given any matrix, we can compute the determinants, okay? And we can also compute the upper left submatrix determinants. Alright, so we will do some examples in the next videos, okay? Alright, so that's why when you want to check whether a matrix is positive definite, first you want to make sure it is real and symmetric. And then you can check whether all the upper left submatrix have positive determinants. If yes, then this matrix is also positive definite. Okay? Next, if A is symmetric positive definite, there is a very convenient form of the LU factorization called the Kolsky factorization, for which U is the L transpose. So that is A is L times L transpose. So now L is a lower triangular, but L transpose is actually an upper triangular because we flip it up across the diagonal. Okay? So now we mark only n times n plus 1 over 2 storage locations are required rather than the usual n squared. So do you remember our last examples? How many unknowns are there? We have a 3 by 3 matrix, right? And we have 9 unknowns. We have 6 unknowns for the L. We have 3 unknowns for the U. So we have 9 unknowns. But the Krauss method says that the U is actually the L transpose. So which means we have only these unknowns. So we have only 6 unknowns if we have a 3 by 3 matrix. But what if we have an n by n matrix? Okay, what happened? Alright, so if we have an n by n matrix, let's say A11, A1n, AN1, ANN, right? So the original Krauss method or Doolittle's method, we have n squared unknown, right? But if we use the Kolsky's method, then the diagonal elements and the lower diagonal elements is going to be our unknown, and the upper ones are the zeros, okay? So how many number are there? Well, let's look at the number of entries in the rows. The first row, we have n of them. Second row, we have n minus 1 of them. And the last row, we have 1 of them. When we add them together, what happened? We have 1 plus 2 plus plus n, right? And the formula of this guy is n times n plus 1 over 2. Why is that? If you call this guy is S, this guy is also S. Well, when you add those together, the left hand side you get 2s. Here, see, this is n plus 1. Here, this is n plus 1. And this one is also n plus 1. How many copies of n plus 1 are there? There are n copies of n plus 1. That's why this guy is n times n plus 1. So now S is just n times n plus 1 divided by 2. So this is how we get those formula. So now with the Kolsky's method, only n times n plus 1 over 2 storage location are required, other than the usual n square, okay? And so furthermore, If A is not positive definite, the procedure may encounter the square root of a negative number in some stage of the computation. And we don't want to do that, right? We want to avoid them because the square root of a negative number is a complex number. And in our course, we want to work with the real numbers. All right, so let's continue. Okay, so let's find the LU factorization of the following matrix using the closed keys method. Okay, so first of all, we can see A is symmetric, right? This is like the mirror, -1, -1, 2, 2, 0, 0. So we can see A is symmetric. Okay, and how do we check is positive definite? We want to check all the upper left submatrix has positive determinant. What are the upper left submatrix? Well, first, 1. Determinant of 1 is 1. Good, it's positive. And then increase the size. This guy, determinant of 1, -1, -1, and 5. Well, cross multiply 1 times 5 minus 1 times -1. So that's 5 minus 1 is 4. You see, this guy is also positive. Good. And then what's left is the determinant of A. What is the determinant of A? Do you still remember how we compute the determinant of 3 by 3 matrix? If you forget, let me review with you, okay? So we have 6 different ways to do that. We can pick any row and any column and do a cofactor expansion. And usually we pick the row or column deck with a lot of zeros. So in this case, we can either use the last row or the last column, they're the same. Okay, and then we put some sign to it. Well, the sign, the 1 entry is always positive, and then it alternates. Well, so then this is negative, this is positive, this is negative, this is positive. So now what do? We use +2 times the determinant of the submatrix by deleting the first column and the last row. So we have -1 and 5, 2, and 0. And then we have -0 times, we don't really care because 0 times whatever is 0. But in order to let you know, the minus is the submatrix by deleting the last row and the second column. So we get 1 and -1 and 2 and 0. Let me erase this sign here because it's confusing. Okay. Alright, and then we have +14 times the minus. The minus is this guy. 1 minus 1 minus 5, 1 and 5, right? So we get 2 minus 1 times 0 is 0. Then we have -2 times 5 is 10. -0 is gone. 14. 1 times 5 minus 1 times -1 is 1. So -20 plus 14 times 4. 14 times 4 is 56, right? So the answer is 36. You see, all of the upper submatrix has positive determinants. So A is positive definite. So far, so good. Okay, now we can start. Okay, we have check. A is positive definite, and then we can find the LU factorization using the Kolsky's method. So what is that? Let me use a different color here. So now you can see right now we are doing the LU factorization. So we set it up like L. So L is L11, L21, L22, L31, L32, L33. So this is a lower triangular matrix times L transpose. So just flip it on top. That equals A. A is 1 minus 1, 2, minus 1, 5, 0, 2, 0, 14. So far, so good, everybody? Okay. Here, you see, we have, okay, so let me show you here. Let's do the 9 position, okay? So first we use the first row times the first column. So L11 squared equals 1. So L11 is, I know the answer is plus minus 1, but here we only pick the positive number. Okay, so we pick L11 is 1. So this is the only place when you take a square root, you can just take but the positive number. And why we can do that? Because A is positive definite. Okay, so we can pick it like that. And then next we have the first row times the second column. So we have L11 times L. So is L11 times L21 and plus 0 times L22. That equals minus 1. Because L11 is 1, so L21 is minus 1. And then we can use the first row times the last column. L11 times L31 equals 2. So L11 is 1, so L31 equals 2. So far, so good, everybody? And then we can use the second row times the first column. L21 times L11 equals minus 1. And L11 is 1, so we get L21 equals minus 1. And you see this guy is the same as this guy. And actually, this guy will be the same as this guy, and this guy will be the same as this guy. So it is enough to just look at the right upper corner entries, okay, or equations. Okay, so that's why we don't need to consider those. We don't need to calculate those. We just give us the same equations. Right, so let me erase here. Okay, but I hope you know the reason why we only need to check these guys. Okay, this one corresponds to second row times second column. So L21 squared plus L22 squared equals 5. L21 is 1, minus 1 squared is 1, plus L22 squared equals 5. So L22 squared equals 4. L22 plus or minus 2, but we only pick the positive. So it's positive 2. And then here we use the second row times the last column. L21 times L31 plus L22 times L32 equals 0. L21 is minus 1, L31 is 2, L22 is 2, L32 is our unknown. So you can see both sides divided by 2, move the negative 1 to the other side, we get L32 equals 1. So far, so good, everybody? Okay, and here we have the last row times the last column. So L31 squared, and we plus L32 squared plus L33 squared equals 14. L31 is 2, 2 squared is 4. L32 is 1, 1 squared is 1. And L33 is our unknown. Oh, so you see L33 squared is just 9. Then L33 is plus or minus 3, but we pick the positive. We pick 3. Okay, so finally, what is L? Okay, a suggestion for you is instead of calculating this box, instead of calculating this box, it is better to calculate these positions. Okay, and then you can directly put those positions inside the L. Okay, but now we can still get it 1, but L21 is actually here. L31 is actually here. And then these are 0. Okay, that one L22 is here. L32 is 1. L33 is 3. So A equals L times L transpose. So far, so good, everybody. Yeah, because we already calculate these guys, so we keep it this way. But for now, okay, suggestions. Okay, when you compute, you compute this guy. Okay, compute this guy. All right, so you will get the similar equation. So this guy will go here, this guy will go here, this guy will go there. So it's just the same set of equations, but this guy match with our L, the spots of the L. Okay. So far so good, everybody. All right, so that is the Kolsky method. So now we have talked about 3 methods. The Doolittle's method, we assume the diagonals of L are 1. The Krauss method, we assume the diagonals of the U's are 1. And the Kolsky method, in order to apply that method, the matrix has to be symmetric, real, and positive definite. Okay? But if the problem that didn't require you to check whether the matrix is positive definite, then you don't need to check it. Okay, you just need to go ahead and use the Kolsky method to find the LU factorization for it. Okay, and in this case, we just need to set up the L because U is L transpose. So here for a 3x3 matrix A, we only need to have 6 unknown. Okay, and the next video, we will continue to talk about positive definite matrix and the strictly diagonally dominant matrix. So see you soon. Bye.